So today I will focus on. Well, maybe let me let's see. Well, anyway, maybe let me just write here. So today I will focus on hyperfunction symmetry and faces. Okay. So I've already briefly mentioned hyperfunction symmetry in a previous lecture, but let me just write down the formal definition. So a Q-function symmetry is generated by a codimension Q plus 1 operator. So here codimension is with respect to the spacetime. Okay. And a Q-function symmetry can act linearly, so it acts linearly, or acts as linear representation. So maybe let me. Acts as linear representation on Q-dimensional operator. Okay. So for example, if Q equal to 0, then this is the ordinary symmetry. So if Q equal to 0, this is the ordinary symmetry. Okay. And the action can be represented pictorially as follows. So let's say this is your Q-dimensional operator, O. So I may use a small q to say it's Q-dimensional. And you can wrap the operator by the symmetry generator. So let's say this is your topological codimension Q plus 1 symmetry generator. So maybe let me call generator U. Okay, so generated by operator U. Let me call it U. Okay. Hello, can anyone hear me? So the operator, the Q-dimensional operator can be enclosed by the generator of the Q-function symmetry. And because the generator is topological, that means that you can deform it. So in particular, you can try to move the operator outside the operator O. So you'll become another operator of Q dimension, and then just move it outside. Okay. And then you can, and if the shape is say of a sphere, then you can shrink it to a point. Okay. So in this way, the operator can transform. Sorry, the symmetry can transform a Q-dimensional operator O to another operator O palm. And in general, you can say that it's a representation. So you can say this is a matrix times the representation vector. Okay. So one important property for hyperfunction symmetry is that if the symmetry is invertible, maybe let me write here. So for invertible hyperfunction symmetry, so here invertible means that the fusion outcome of any two hyperfunction symmetry generator is unique. So for invertible hyperfunction symmetry, the fusion is a abelian group. So to understand this, you can try to fuse a generator A and generator B. Okay. So those are generators of the hyperfunction symmetry. So here higher means that I should say that higher means that Q is greater than. So higher means that Q is greater or equal to 1. So it's not the ordinary symmetry. Now, because the generator has codimension higher than codimension higher than 1, so we can move this A to the other side of B. So this is the same as B and A. Okay, so we just deform this topological operator A like continuously using this extra dimension, extra direction, and pass through A such that the order is exchanged. Okay. That tells you the fusion of A and B is the same as the fusion of B and A, and therefore the fusion group is abelian. So that's the first comment. Okay, so now because I'm going to talk about phases, and the standard phase, the standard way to describe phases is using a Landau paradigm. Landau paradigm. Okay. So what Landau paradigm means is that it describes a class of phase transition such that on one side, so let's say this is your phase transition. Okay. So such that on one side of the phase transition, the symmetry is broken, spontaneously broken. So let's say this is spontaneously broken symmetry. In general, yeah. So I'm here just describing Landau paradigm in general, but let's say it's Q-form symmetry. Well, the other side of the transition, the symmetry is unbroken. So unbroken symmetry. So that's a general description of the Landau paradigm. On one side of the transition, you have broken symmetry, while on the other side of the transition do not have the symmetry is not spontaneously broken. Okay. So how do you apply this kind of Landau paradigm to the hyperform symmetry? So we first need to understand what what happens when the hyperform symmetry is spontaneously broken. Can I use this or? Okay. So spontaneously broken hyperform symmetry. Okay. So what is spontaneously broken hyperform symmetry means that let's say here I take a symmetry to be Q-form symmetry. So it means that the symmetry acts in the IR. Symmetry acts on some Q-dimensional operator OQ in the IR. Okay. So a spontaneously broken hyperform symmetry or Q-form symmetry means that in the IR you are going to find some Q-dimensional operator O such that the symmetry acts on them. So I'm going to give you some examples later. In contrast, if the symmetry is unbroken, means that there is no such operator. So this is broken, unbroken, no such operator acted on by the symmetry. Okay. In IR. Okay. So whether the symmetry is broken or not tells you whether the IR has like Q-dimensional operators charged under the symmetry. Now, importantly, when the symmetry is unbroken, even though the symmetry does not act on Q-dimensional operator, it doesn't mean that the symmetry does not act. I will give you a few examples later. So, in an intermediate energy region, you can characterize those broken or broken by the parameter law and area law of the Q-dimensional operator. So let's say you have a Q-dimensional operator OQ that is charged under the Q-form symmetry, and then you compute the expectation value of the operator when the operator is very large. Okay, so margin is supported on some Q-dimensional manifold N. Maybe let me. Okay. So when the Poisson function decay by the area, sort of hyper area, so minus area of a like one-dimensional higher manifold that bounds the manifold M. So let's say here M is a two-dimensional manifold, and imagine this MQ is bounded by another manifold. Let's say this is V of one dimension higher. If the expectation value decays by the volume of this one dimensional higher manifold or the area, so let me just put quote unquote of this 2 plus 1 dimensional manifold, then in the IR, this operator, this expectation value will just become 0. Okay, so becomes 0 in the IR.
So
yeah.
Maybe it's a silly question, but in a general QFT, what's a good scale to measure area against? Like a good physical scale, so you get dimensionless number?
Well, I mean, it depends on the, I mean, here you already have a length. I mean, when you specify the manifold, you put it on some two-dimensional submanifold, right? Here you already have like a size of the submanifold. Yeah.
I see, but so I mean to say, so okay, say you have some really gauge theory,
right?
And this area is things like that.
Right, it depends on like the various couplings in your theory. Yeah, you can also have some emergent like dimension transmutation occurring QFT in general. Yeah.
Okay, so I could use some function of the coupling constant.
Yeah, in general, it'll be some function of coupling. Yeah. Right. Okay, so here we are going to say the question this two-dimensional operator will be area low because the Poisson function decay not just by the like a volume of this operator that support volume of the submanifold that support the operator, but by some bounding submanifold one dimension higher. Okay, so this is so-called area low. And if the operator obey area low, it does not break the high-function symmetry because it just becomes 0. Okay. On the contrary, if you find an operator whose expectation value does not scale with the like area of or the volume of the one-dimensional higher manifold, but by the volume of the manifold itself, then it's called parameter law. Maybe let me erase this. So, contrary, if you find that, it can be given by, or maybe, yes, quote unquote, or the size of the submanifold itself. Then you can add some contour along the manifold. You can add some contour on this two-dimensional submanifold such that this Poisson function becomes a constant. So it can be improved to a constant, can be improved to constant by local counter term on some manifold, and that's approach the operator. Then in such case, the symmetry is spontaneously broken. So if you find out there's a two-dimensional operator or the charge on the symmetry obey parameter law, then you can conclude that the symmetry is spontaneously broken. Spontaneously broken. Okay. So you can think about these two behavior as describing whether the operator confine or not. So if the operator obeys this kind of area low decay, then we can say that it confines. Well, if the operator obeys this kind of parameter law, then it is deconfined. Deconfined. Okay. So for example, if Q equal to 1, let's see. Let me erase this.
So the final image comes in like Wilson-Max reports, right?
Oh yeah, I'm going to give you an example of one-function symmetry that will match to the more traditional confining definition. Okay, so let me just give you an example equal to 1. So let's say you want to describe one thing symmetry. Okay. So so here, so let's say you have a non-operator. So let's say you have a your OQ equal to some Wilson line, for example. Okay. And so you can describe the following Wilson line configuration where you have a like a pair of a pair of clocks like a Harvey probe particles. So let's say this is your word line. So word line. So like a pair of Harvey probe particle. And you want to know what what's the potential that like between these two probe particles. Now, if the potential, so let's say the distance, so let's say the separation is L, okay, and you that the particle propagate for a time t, so this is time, okay. Now, suppose the two probe particles feel a linear potential, like very strong attraction that grow linearly with the distance. Then this configuration will have energy L times t, like proportional to the distance times the time where you do the evolution. Okay. So this is for linear potential, like V of R grows with R. Okay. So if these two particles like strongly attracted to each other by linear potential, then energy will be proportional to like the area in space-time. So you have like these two parallel Wilson line, and you have a like this strip that bounds the Wilson line. And if the potential is linear, then energy will grow as the area of this like space-time strip. Okay, and therefore this configuration will decay as usually like area, okay, times a constant. Okay. So this is basically the traditional confinement picture where you have like strong like linear potential, and then this configuration of Wilson line will decay by the area of space-time. Okay, so that's why this is related to the area law. And more generally, if the excitation is not if the operators are not line operator, but like more general higher dimensional operator, you can have a like generalized area law that corresponds to confinement. Okay. And generally, if the potential is a constant, then you will have parameter law. Okay, so let me just give you a few examples. Yeah, sure.
In the deconfined case, the integral might be like L plus 2. The 2L plus 2t would be the perimeter that's like square.
So here I'm thinking like to infinite. Well, I can think of as infinite extended like parallel Wilson.
Yeah. So I mean, if you wanted to write down the perimeter, would it look like e to the minus?
Well, then we'll have to close somewhere. I mean.
Yeah. I guess my question is how do you do that in the same times? Is it easy to see?
I mean, just that. Well, I mean, if you have low counter like scale with the size, right? So let's say you have a like q-dimensional. Well, let's say you have a if you know something like scale with the volume of a q-dimensional manifold, then you can always write some like counter on on this q-dimensional submanifold that also scale with the like a volume of this q-dimensional submanifold. Yeah. But however, if they but however, you cannot use counter to cancel something scale with like one dimension higher. Yeah. Right. Okay. Well, before I go to example, are there any questions about the definition? Okay. So let me just go to some example. So let me discuss a simple U1 gauge theory. Okay, I'm going to erase this. So let's say we're going to consider 3+ dimension U1 gauge theory. So there's a gauge field A. So there's a gauge field A. Okay. So the theory has many line operators. So line operators. Okay. So there are Wilson line operators. Wilson line operators labeled by integer, so which is the electric charge. Okay. And there are also 't Hooft line operators. 't Hooft line operator. So you can define 't Hooft line. Well, you can think of 't Hooft line as monopoles. Namely, it's defined by the flux through a two-sphere that enclose the monopole. So monopole is a point in space and extend along the time direction, so it's a line. And the flux can be so it's 2 pi times the integer, where integer is the magnetic charge. So QE is the electric charge. Okay, and Qn is the magnetic charge. Okay. And correspondingly, there are two U1 one-function symmetries that act on those line operators. So there's a U1 electric one-function symmetry. And the U1 electric one-function symmetry has a current. So the current base is given by the electric field. So it's given by dA times the coupling constant. And there's also U1 one-function symmetry that acts on the 2 lines. This is E. Okay. And the current is given by the dual field strength, where the star is the Hertz dual. Okay. And so the electric one-function, so current for the electric one-function symmetry conserved by the equation of motion, while the current for the magnetic one-function symmetry conserved by the for a topological reason by Bianchi and LonTI. Okay.
So what is the magnetic current?
Oh, this is dA.
dA. If I wanted the total line to be a defined for delta function?
Yeah, so if you want, well, I mean, if you want to insert to find a perfect goal, you have to modify your gauge field such that there's some like delta function. Left, yeah. I mean, you'll have to modify the gauge field. Yeah, doesn't that modify the gauge field? So if you want to insert a fly, like at some point, like if you want to insert a monopole at some point in the particle, it tells you that the flux, like the flux on any sphere that encloses the 2 fly has to be like 2 pi times a like fixed value. Then you can only integrate over the field configuration such that it has this property.
Yes.
Yeah.
So
yeah. Main can explain by some delta function. Yeah. Right. So because the theory is free, so we begin for free. When theory, now theory is free, and therefore anything you write down will be presented in the infer, right? Because the theory is free and there's no algebraic flow. Okay. Now because there are line operators acting by the one-function symmetries in the IR, so that tells you that those one-function symmetries are spontaneously broken. Broken. So acts on lines in IR. Okay. And in particular, those Wilson lines and 2 lines are deconfined. Okay. Well, because the theory does not have any algebraic flow, so they're present both in the UV and in IR. Now let's break the U1 gauge group down to a discrete subgroup, such as Z2. So maybe let me erase this. So let's break the U1 gauge group to Z2 by adding some Higgs scalar. So by Higgs scalar 5. Okay. And then we can examine what happens to those one-function symmetries. Okay. So here I'm going to take the Higgs scalar to have charge 2. So okay. So I can think of this Higgs scalar as a Cooper pair with charge 2. Now, importantly, because now you introduce a elastic matter, you introduce a Higgs scalar of charge 2, the Wilson line of charge 2 can now end on the scalar. Okay, so this is your Wilson line, or maybe let me give them a name. So let me call this W. So this is W. W. And this is N, capital N. Okay. So the Wilson line of charge 2, maybe let me not use the Q here. So Wilson line of charge 2, charge 2, can now end on the Higgs scalar, because both of them have charge 2. But because the Wilson line can end, so that tells you that the symmetry that transforms the charge 2 Wilson line will not be explicitly broken. And the reason is that it can, suppose you enclose the, actually it's a different color. So suppose you enclose this charge 2 Wilson line by a topological operator that drains the symmetry. So this is a symmetry operator. Because the symmetry operator is topological, so you can just continuously deform it, like pass through the endpoint here, and then just unlink with the Wilson line. So you can deform it such that symmetry becomes unlinked with the Wilson line. And so that tells you that the Wilson line cannot have any charge with the remaining symmetry, because the Wilson line can have an endpoint. So,
sorry, if I understand topology you can put it out. What if you wanted to shrink it so that it does have a contact term with the line first? Does that imply that the contact term must be true?
Which contact term?
The yellow circle where it is now. It's the implication that there must be a trivial phase picked up if you check the yellow circle.
So you can shrink the yellow circle in two ways, and they are equivalent because it's topological. So one way is to just directly like shrink the yellow line, and another way is to move the yellow line pass through the endpoint and then shrink it.
So in the previous case, you shrunk the yellow line and pick up the ETI alpha.
Yeah, you pick the transformation of the operator under the symmetry. Yeah, some phase ETI alpha. Yeah.
But now the phase is trivial.
Right. So that's the argument that phase must be trivial. Yeah. So maybe let me just repeat the argument again. So there's two ways to shrink the yellow line. So one way is to just use the definition. So let's say this transform by so if you shrink the yellow line, you got a phase. The phase tells you like how much charge the symmetry transformed the symmetry. So how much charge the operator transformed the symmetry. The second way is that you move the yellow line pass through the endpoint and then shrink it. I mean, here it's just the same. Okay. So that then you conclude that the phase has to be 1. Okay. Okay. And this breaks the electric one-function symmetry from U1 down to Z2. So this is explicitly, so the U1 electric one-function symmetry is explicitly broken to Z2. Okay. So this is explicit. Okay. That's right. So that's why this is consistent with the conditions here. Yeah. So the remaining unbroken Z2 symmetry actually on charge 2 versus 9, and therefore the phase here is actually 1. Therefore, this is consistent with this deformation. For all the other elements in U1, you'll have a contradiction here. Yeah.
I'm confused why it's broken to Z2 because I understand it's just even Wilson lines now you screen and it goes with but to say it's broken to Z2, does that mean the symmetry defects have the 2 parameters basically? As
that's right. As opposite to like continuous like U1 parameter.
So what if they're sorry, I don't understand why is that the case?
Right.
2 parameters for those symmetry defects.
Well, maybe let me just put it this way. So let me just run the argument again. So let's say this is your symmetry generator U, and you implement a transformation by theta. Okay, so theta is a U1 parameter, the angular parameter. Okay, and this white line is charge 2. Okay. So here you'll have a phase given by e to the twice theta. So 2 is because this is charge 2. So this is charge 2, charge 2, and charge 2, charge 2, charge 2. Okay. And by this manipulation, you have to conclude that e to the twice theta has to be 1, right? Okay. And therefore, the only consistent transformation parameter is theta equal to 0 pi, which is the Z2 subgroup of U1.
Okay, so but then that tells you even for other rules or in the whole theory, you can only have Z2 U.
Right.
For consistency reasons.
Sorry, say that again?
To say, if you had another rule, so maybe charge 3 rules.
Right. Then you transform non-trivially under the Z2 subgroup.
So that's another rule. But in the charge 3 rules 9, can you still write a U theta for a U1?
Yeah. So U theta is universal. U theta does not care about which version, and U theta is just a symmetry generator.
So that's what I mean. So you still have the other U theta. So when you write that symmetry breaking, that's not to say the global symmetry, the entire theory is broken down into Z2.
It is. Okay. So this argument tells you that if theta is not 0 and pi, then the configuration 1 cannot be configuration 2, right? Because because when you violate this equality, it tells you that 1 and 2 are different, right?
Oh, I see.
But then that implies that the symmetry, this yellow line that generates the symmetry, cannot be topological, right? And therefore, there are no longer symmetries necessary. So that's why all the other U theta are explicitly broken, because they are no longer topological. Yeah. Are there other questions? Okay. So this is for the electric one-function symmetry. And now we can ask what happens for the magnetic one-function symmetry. Let me erase this. So first of all, you still have magnetic one-function symmetry. So still has U1 magnetic one-function symmetry. Because the two line operators cannot end because even if you introduce a Higgs scalar carry electric charge but does not carry magnetic charge. Okay. And therefore, you still have the full U1 multi-one-function symmetry. Okay. However, because you break the U1 down to Z2, I mean, let me first say what I mean by U1. Because you break the U1 gauge group down to Z2, and the Z2 gauge shield does not have any multi-flux on S2, so integral of dA is now 0. So that tells you that the theory, after you break the U1 gauge group down to Z2, no longer have two lines. So only two lines are confined. Okay. Because you no longer have any multi-flux. Okay. So that tells you that before you fix the gauge group down to Z2, you have to confine two lines with spontaneously broken U1 multi-symmetry. After you fix the gauge group down to Z2, the two lines are confined, and the multi-one-function symmetry is now the unbroken. Okay. And you can ask, like, how does U1 multi-symmetry, U1n act in the theory? Well, one way to think about how the symmetry acts is by coupling the theory to a background gauge field. We can introduce a background two-phone gauge field. So the gauge field for a one-phone symmetry is a two-phone gauge field because the transformation parameter is a one-phone. Okay, so first of all, it's a two-phone gauge field. And the gauge field couples to the current. So usually for the ordinary symmetry, you write down a coupling like mu j mu. So this is for ordinary symmetry. For the one-phone symmetry, the coupling is similar. Namely, just couple the background gauge field to the current. Okay. And here the current is 1 over 2 pi the whole dual of dA. Okay. So using similar reasoning, you find out the coupling is 1 over 2 pi of dA times b. So there's a wedge product here. Also, in the deep infrared, when you fix the U1 gauge group down to Z2, you can dualize the phase of the Higgs field, such that the theory effectively is described by the following action. Okay. So here the small b here is a two-phone, which is dual to the phase of Higgs scalar. And you can think of this small b as a Lagrange multiplier that constrains the holonomy of the gauge field A to be 0 pi. Okay, so this is consistent with breaking the U1 gauge group down to Z2. Okay.
Can you say how you show that the two lines are confined?
Right. So the two lines are confined because there's no when the gauge field is broken to Z2, the field strength is locally trivial. In particular, if you integrate the field strength over like any two sphere, you got 0. So there's no longer any two lines in the theory after you break the U1 to Z2. Yeah.
That's good. I thought the confinement was the statement about area.
Right. So if the operator open area low, in a deep area, the operator will just be 0. Yeah.
Oh, okay.
So there's an important difference between parameter law and area law. So area law, so for parameter law, you can always make it like a constant law by adding local counter term. So you still have a non-trivial like one-point function in the IR. But for area law, you cannot cancel the area law by a local counter term, and therefore it has to be 0. Yeah. Okay. So there's no. Let me just write again. No 2 flies. Okay, so and therefore in the IR, I just add these 2 terms. And if you take the equation motion of A, you'll find out the operator. So this operator, which describes the vortex, in the Higgs space, actually carries charge a half under the one-form symmetry. So carries charge. Okay. So, well, this is just well, you can see there are 2 terms. One is AdB, the other is AD capital B, and therefore equation motion of A was at like 2 times small b equal to capital B, or like small b equal to a half of capital B. So that's why this operator carries charge a half under the U1 one-form symmetry. And this operator corresponds to a vortex. So this is the this is called a vortex. So in this example, you find that the U1 magnetic one-form symmetry is not spontaneously broken, but it still acts non-trivially in the infrared. And it acts non-trivially in the infrared by saying that the vortex ring carries charge 1/2 under the under this magnetic one-form symmetry. So this is called fractionalization. Okay, so what this example shows so far is the following phase diagram. Let me erase this.
So the vortex is two-dimensional.
Right. So here, this is integrate over like a surface. Okay. So it describes the vortex string excitation or vortex loop excitation.
How do you link the one-form generator with the surface?
It does not. So first of all, this is 2-dimensional. So you have to discuss how the symmetry acts on a 2-dimensional object.
Yeah.
Right. Right. So the idea is that the idea is the following. Let's see. Okay, maybe let me just draw here and then erase it. So the idea is to consider junctions of the one-form symmetry. So in a previous lecture, when I discussed the like anomaly for U1 symmetry, I have drawn this kind of diagram where you have a U1 symmetry transformation here, let's say by some θ1, and U1 symmetry transformation by θ2, and they fuse into U1 symmetry transformation θ1 plus θ2, and let's say you restrict the range to be between 0 and 2 pi. Okay, and now so here each symmetry generator for one-form symmetry has codimension 2. So in 5000 dimension there are surface. So it's can think of each line as a surface. Each line as a surface. Well, let me just try to draw a 3D picture. think of as like three surface made at a junction, which is a line. Okay. And when and then you can link the junction. So junction now is a line, and then you can link the junction with the surface there. Yeah. So that's how the transformation is done.
Okay, so that means that. Sorry. So that surface.
Let me just be concrete. Okay, so let me give you a particular example of transformation. So so let's say if you transform, so let's say this surface implements the pi transformation. It does not be pi, but let's say I just put it to be pi. Okay, then this is 0. Okay, and then there would be some line here. Okay, and the statement is the following. So if you you can try to imagine in your head that you're linking this junction with the surface there. I mean, I cannot draw like 4D picture, but I just imagine. And the statement is that the junction will link with the membrane such that the linking produces a -1. Yeah, okay. So that's for the mass, the transfer.
Point per sphere, for example, the two surfaces. And then I want to ask, that surface must intersect the pi surfaces as well, right?
Yeah, right. Yeah. So they intersect in such a way that if you link the junction with the surface, you get the mass 1. Yeah. You can also think about the surface as a so the surface corresponds to like a wall sheet of some like loop excitations. And the statement is that these loop excitations carry charge 1/2 under the U1 symmetry. Yeah. So this is similar to like a fractional quantum effect where you have some quantum particles that carry like fractional charge under ordinary U1 symmetry. But now you have some loop excitations instead of particle excitations that carry charge 1/2. Okay, so let me just draw a phase diagram. So this axis is the Higgs coupling. And here, so let's say phi condenses. And here phi does not condense. Does not condense, okay, here. So when phi does not condense, you just have the free U1 gauge theory, and you have broken 1m. Okay. So now let me just focus on the U1 magnetic one-function symmetry. So when phi does not condense, you have a free U1 Maxwell gauge theory. So you have a spontaneously broken U1 magnetic one-function symmetry that's on the tooth lines. When phi condenses, as I said earlier, you have unbroken U1 magnetic one-function symmetry. So here, broken means spontaneously broken. Okay. But the U1 magnetic one-function symmetry still acts in the infrared by fractionalization. So there's some fractional excitation, fractional loop excitation. Okay. And this is an example of a Landau transition for U1 magnetic one-function symmetry. So on one side of the transition, you have broken U1 magnetic one-function symmetry. Well, on the other side of the transition, you have unbroken U1 magnetic one-function symmetry. So here, this is a Landau transition. Landau transition for U1 magnetic one-function symmetry. And this is basically describing a like a massless scalar coupled to U1 gauge theory. So this is like a scalar QED, U1 plus scalar, mostly scalar. Okay. So yeah.
What's on the axis?
Right. So this is, so you can think of it as the well. Let me just write down the interaction of Higgs field explicitly. So the Higgs field has a potential. Okay. So this is like mu square, phi square, and then plus lambda over let's say 2 and then phi to the 4. Okay, something like that. So we can take the Higgs field to have a Kotic potential. So and the Kotic potential will have a single minima if so here lambda is positive. So here I'm going to fix lambda to be positive and then adjust the mu square here. Or maybe let me not even say it's mu square, just some parameter mu, okay? And then here the axis is mu. Okay, the axis is mu, okay? So if mu is positive, then the potential will be minimized by phi equal to 0. Right, because the potential will be strictly non-negative, so minimize phi equal to 0. And this corresponds to the case where phi does not condense. So, well, maybe let me switch the sign a bit. Okay, this is mu positive. And when mu is negative, the potential is going to have like many minimum, right? So they're going to be, so this is the case where phi condenses. So I can, let me try to draw the, just try to draw the potential, because I can erase this. So when mu is negative, you have the like standard like masculine half. Well, I'm not sure how to draw it. Something like this. Okay, well, so okay, let me just draw it as a rotation curve. Okay, so imagine there are okay. So you start from this like 2D slice of the potential and then just rotate around the vertical axis. Okay, so this is the potential when mu is negative, and therefore you have this degenerate minimum, and that's when when phi condenses. Yeah.
And like, where does phi condense or not matter?
Phi condenses. Well, if phi condenses, then you will break the U1 gauge group to down to a, well, I mean, here I'm taking phi to be charged 2, so I mean, if phi condenses, then you will break the U1 gauge group. Yeah.
Also, does phi need to have a wave in and Wilson
line? Well, so first of all, there are two issues. So first of all, if I introduce any scalar field of charge 2, then I will explicitly break the U1 electric one-function symmetry down to Z2. And this is because if I have a like charge 2 matter, then a charge 2 will like n, and it does not depend on what's the potential of this charge 2 matter. If you have anything that have charge 2, then will like n, regardless of the potential, and then the electric one-function symmetry is explicitly broken to Z2 by this argument. Okay. So that's the first thing. And the second thing is that if the potential is such that the scalar field condenses, then the U1 gauge group is broken down to Z2, and then all the 2 lines will disappear. So 2 lines will confine. And then so that's the spatial thing happen when the when the potential is of this shape, where the scalar phi condenses. Yeah.
Do we know what order the phase transition is?
And this is just U1 gauge field plus some like massless scalars. So you can, well, I mean, you can just say this is the this could describe the phase transition. Yeah.
Like it's in terms of the phase transition.
I mean, it's likely to be, well, it's likely to be first order because of the common Weinberg correction. Yeah. Yeah. Okay, so maybe it's a natural stopping point. Maybe we can take a break for like 10 minutes. So I will continue to discuss a few examples of like diagnosing phase transition or phases using Halford symmetry. So beta okay. So a classic example is QCD. So let's say you consider pure SU3 gauge theory. And let's say we are considering theory in 3% dimension. So the theory has a Z3 center, one thing symmetry. Well, maybe before doing that, let me first say that the theory has Wilson line operators. It has Wilson line operator that transform as some representation of SU3. So as some representation of SU3. Okay. Now theory has these three center symmetry. These three. So these three, you can think of these three as part of like the center of SU3. So these three one-function symmetry. And the one-function symmetry transform the Wilson line as follows. So if I have a Wilson line representation R, then you transform the Wilson line according to the like a chirality or like the so let's say you have representation labeled by some Young table, and so this is some Young table. And the Young table has number of boxes, so there are let's say R boxes. Okay. Then the Wilson line will transform as like 2 pi I over 3 times the transformation parameter times the number of boxes. Okay. So in other words, the Wilson line interpretation R carry a phone charge R. So WR carries one phone charge R mod 3. Okay. So this is a one-function symmetry in the theory. Another way to understand one-function symmetry is that you shift the you transforms the SU3 gauge field by a diagonal pair. So you shift A by something in the diagonal, like D, like 1, some like d theta over 3. Okay. And you shift the SU3 gauge field by something proportional to identity, but it is a flux connection. So this is a flux connection. It's a Z3 flux connection. Okay. And then you induce the Hsin transformation on the Wilson line, as I described before. Okay. Okay. So now let's consider SU3 gauge theory at finite temperature. It is believed that at 0 temperature, the SU3 gauge theory confines. So temperature So at t equal to 0, it's believed that the monopole condenses, and then the Wilson line confines.
What do you mean by condense?
Well, so I mean in a similar way as like in the electromagnetic dual version, it's like you have a Higgs field, then the electric charge condense. So then you can just try to dualize it. Yeah. Okay, so it's believed that at t equal to 0 or at low temperature, the Wilson line confines. So here this is just some belief based on numerical simulation. And when the temperature is very high, it is believed that everything will deconfine, like Wilson line will be deconfined. Okay. Now, the Wilson line carry charge under this Z3 one-function symmetry. So at t equal to 0, the Z3 one-function symmetry is unbroken. So maybe let me draw a phase diagram. Let me just erase here. So let me draw a phase diagram for temperature. So this is temperature. Okay. So when temperature is very low, even t equal to 0, you have unbroken. So you have unbroken Z3 one-function symmetry. And then here you have confined Wilson line. Okay. And it's believed that when temperature is very high, eventually the Wilson line will become deconfined. And the Wilson line, when the Wilson line is deconfined, the Z3 one-function symmetry is spontaneously broken. So there's a broken, or SSB, Z3. This is 3 one-function symmetry. And again, there is a confinement-deconfinement transition described by LonTI paradigm. LonTI paradigm for Z3 one-function symmetry. So the fact that you have a broken Z3 one-function symmetry when temperature is very high and unbroken Z3 one-function symmetry when temperature is very low tells you that there must be a phase transition, a sharp phase transition in the middle. And there's a sharp phase transition because you cannot break like Z3 partially, like break Z3 to like Z2.5 or something. Now, in contrast, suppose now you consider QCD with matter with clock. Let me just use the Rockwell here. So, in contrast, so if you consider SU3 with clocks, with fundamental clocks. Now, if you have fundamental clocks, the Wilson line can end. So this is fundamental. Okay. So if you have fundamental clock in the theory, then the Wilson line can end. And that tells you that these three central one-function symmetry in the presence of clock will be explicitly broken. So there's explicitly broken these three one-function symmetry. Okay, Now, when the temperature is low versus when temperature is high, you still have similar behavior of Wilson line. So you can say Wilson line confined on low temperature and deconfined on high temperature. But now, because there's no longer a symmetry that distinguish these two behavior, you actually find a crossover instead of a transition. So if you break the symmetry, then this phase transition will just disappear. It becomes a crossover. So it becomes a crossover if you do not have any one-form symmetry that distinguish these two behavior of the Wilson line. So this tells you the importance of having a symmetry that distinguish these two behavior. That can tell you there's a sharp phase transition in between the two. Okay. So here you'll find out. So there's a there are numerical study shows that there's no phase transition as you increase the temperature, but instead a crossover. Okay.
Is it possible for the charge factor to give you new symmetry?
It could, yeah. But for this discussion, the symmetry does not distinguish these two behavior of the Wilson line. Yeah.
For the Z, the Z.
Right. So that gives you another example of how the high-function symmetry can detect phases. Now let me give you other examples. So another important application for high-function symmetry is to describe the topological order. Let me first explain what is a topological order, loosely speaking. So a topological order can describe the following correlation. So you can have an excitation or a pair of excitation, excitation 1 and excitation 2, such that there's no local correlation between excitation 1 and excitation 2. So you can move excitation 1 and excitation 2 like with various distance, but there's no local interaction. However, there are global interaction that depends on topology. So if you move the excitation 2, which is very far away from excitation 1, and such that you move the excitation 2 around excitation 1, like you break these two excitations, then you can find a non-trivial phase or non-trivial number. So breaking interaction. And this interaction does not depend on distance. And there's no local interaction between the two. Instead, there's just this kind of long-range global interaction. Okay, so that's the defining feature of a topological order. So this is called remote detectability. Okay. Namely, there's no local interaction between excitation, but if you have any non-trivial excitation, it must be detected by another excitation by this kind of braiding. So this is called remote detectability. Okay. And also, because there's no local interaction, it tells you that you can just freely move the excitation around. So the corresponding operators that create those expressions have to be topological. Operators correspond to the excitations are topological. And because they are topological, so you can think of them as generating a symmetry of the theory. In general, the operators will have higher codimension, so you'll describe higher form symmetry. So higher. So this is just a statement that there's no local interaction between excitation. Now, what's the implication of this kind of braiding for the high form symmetry? Well, it tells you that the symmetry operators must obey non-trivial coefficient function, and therefore the symmetry has to be anomalous. So well, let me just say this is number 1, and this is number 2. And number 1 plus number 2 tells you that you have anomalous high form symmetry. So you can, loosely speaking, relate topological orders to anomalous high form symmetry. So this corresponds to topological order. Now, why do I say loosely speaking? Well, because here you want to say that the symmetry is spontaneously broken. So maybe let me add the parentheses here. So this is spontaneously broken. And the reason it is spontaneously broken is because of this braiding property. So if you have a symmetry that corresponds to excitation 1, namely the symmetry operator creates excitation 1, the braiding tells you that the symmetry must act on another operator that corresponds to excitation 2. Okay. So each symmetry will act on non-trivial operator by braiding in the infrared, and therefore the symmetry is spontaneously broken. So here you have anomalous high form symmetry which is spontaneously broken, and that corresponds to a topological order.
Are you saying it's generally anomalous, or it has to be?
It has to be. Well, it has to be. So here, well, let me just emphasize again. Okay. So the braiding tells you that if you have a symmetry generator that corresponds to some excitation here, it must braid with another symmetry generator that corresponds to another excitation. So that tells you there is a non-trivial braiding relation or braiding coefficient function between those high form symmetry generators, and those coefficient function tells you that you cannot gauge those symmetries, and therefore the symmetry is anomalous. Okay, so that's the logic here. Is it clear? Okay. Okay, so let me just give you a few examples. Well, let me begin with one form symmetry. Maybe, well, actually I can use this. Okay. So we begin with a example of one-function symmetry into Po-Shen dimension. So let me describe the coefficient function in, like the anomaly in more detail. So I want to understand like quad is an anomalous one-function symmetry. Well, here I should emphasize that I have to take a symmetry to be discrete. So I have to add another word here, like this is discrete. Okay. Okay, so so let's understand what's the anomalous one-function symmetry into Po-Shen dimension, like anomalous discrete one-function symmetry, anomalous discrete one-function symmetry. Okay. Now, as I explained earlier, if you have invertible one-function symmetry, then the fusion has to be abelian. So here, let's focus on abelian. Well, let's see. Where's the eraser? So because the fusion is abelian, we can focus on a Zn one-function symmetry. So, and let's ask what kind of topological order we can obtain. Okay. So the Zn one-function symmetry will have a generator. Let's say generator is called A. So n A to n equal to 1. Okay. And we have the and because the symmetry is Zn, it tells you that if you break any line operator here with this n with this A, you got a nth root of unity. So it gives you like e to the 2 pi I times an integer over n times the unlinked configuration. Okay. So that's the definition of a Zn one-function symmetry. And we would like to understand like what are the set of Zn one-function symmetry. Now there is an important property of a one-function symmetry generator into Po-Shen dimension, namely is the spin of the symmetry, and the spin is described by the following configuration. So if you sort of twist the generator in this way, then it will give you a phase. So this is your generator A. It will give you a phase compared to the untwisted version. So you can think of this A as describing like a raw line of a particle, and then this configuration is like rotating the particle by 2 pi. Okay. So this phase is related to the spin of the particle. So now let's try to understand what the possible spins of these particles correspond to the Zn one-function symmetry. Okay. Now, first of all, we use the property that if we fuse this generator A with the inverse, so let me just call it A bar, and give you 1. So we can think of like A and A bar as the lines with opposite arrows, like if this is going up, and this is like the same A but with arrow going down. And therefore, the line A and line A bar should have the same spin. So the spin of A equal to the spin of A bar. Okay. And now let's try to trace this So you can think of the fusion of A and A bar as a like putting together two lines, and then you can twist this this composite lines in similar way here. So well, I'm not sure how to draw it, but let's see. There's a different color. Let's see. Okay. Well, so so you can try to twist this this strip, and then you'll find that there's a linking between the A with itself with A bar. So there's a linking. So there's a linking. And this twist should give you 1 because if you fuse A with A bar, it just gives you the identity. Okay. But you can rewrite this identity into like first you twist the this white line, which gives you 2 pi times h of A, and then twist the yellow line, then you got 2 pi times h of A bar, which is the same as h of A. And then you have additional braiding between A and A bar, which is say nth root of unity. So from this, you can conclude that the spin of the particle has to be some number, has to be some integer number, so let me call it integer number p, divided by 2n. Okay. So p is an integer. Is this clear? Okay. So this condition tells you that the set of Cn one-function symmetries in 2-person dimension can be characterized by an integer p. So integer p describes all the quotient function of this Cn one-function symmetry generator. And the theory describes a topological order that has n particles. Well, maybe let me just use the block hole there. So this is the so-called minimal TPFT or Zn. So it's a theory of n particles. So the set of particles are given by the power of this A, so A to the k, where k like 0 until n minus 1. And the spin of the particle is given by k over 2n. Okay. For some integer p. Okay.
Is that the definition of meaningful?
Yeah.
Have you shown any Cn symmetry numbers?
Right. So any Z1-function symmetry, like by this reasoning, it will be generated by like a generator A with this particular spin for some integer p. Okay. Yeah.
Oh, so you're saying it's minimal because the entire set of lines is just this one.
Yeah. You know, there's actually some condition that tells you it has to be minimal. So, yeah, let me just explain a bit. So here I just define for you as like a set of particles with this kind of braiding, with this particular spin. Now, okay, ask, do they give you a consistent topological order? Okay. Or in other words, does this set of particles obey the remote detectability? Okay. Now it turns out that if you want to require a remote detectability, there must be a condition on this integer p here. Okay. And the reason is that if so let's just say that let me just first write down the condition. So it turns out that P and N has to be co-prime, so GCD N has to be 1. Okay. Now, if there's a non-zero, if there's a non-trivial GCD, so let's say if there's a like L equal to GCD of P and N, then you can find like two particles inside this set such that they break trivially, so then the set violate remote detectability. Okay. So, for example, you can take like A to L. So first let me write down the general braiding of two members in the set. So we have A to the K1 and A to the K2. And there's a braiding by 2 pi of P K1 K2 divided by N. Okay. And therefore, if you choose and therefore, if L is non-trivial, then can choose like K1 equal to over L. So if K1 equal to over L, then like this N in the denominator cancel with this N here. Well, L here can divide N, can divide P here. So then the phase becomes trivial. So it tells you that if this integer P violates this condition, then this set of particles cannot by itself be a consistent topological orders. Okay. Now let me just demonstrate that this braiding relation or this spin of the particle really captures the anomaly of the one-function symmetry. So one way to think about anomaly is just to couple the theory to a gauge field and see whether you can consistently gauge the symmetry. So let me give you an example of P equal to 1. So for if P equal to 1, you can describe those set of particles by an abelian transform theory. So for example, 4 pi. You normally use a different label. Okay. So here, small b is a let's say U1 one-form gauge field. And the theory has Wilson line e to the some integer times integral b, where this I here, where this k here runs from like 0, 1, 2, 3 up to n minus 1. So let me focus on even for simplicity. And those set of Wilson lines correspond to the set generated by this A here. In particular, this symmetry generator A is described by the Wilson line of unit charge. Okay. And the Wilson line of unit charge, it has been 1 over 2n. So there are many ways to see this 1 over 2n. Well, one way is to describe the spin by the modular T transformation of the corresponding to the CFT. But here, let's just say that this basic Wilson line has a spin 1 over 2n, and that corresponds to the case where P equal to 1. Okay. And now let me just show you explicitly that there's an objection to gauging the one-function symmetry in the theory. Yeah, let me use the bubble here.
We still find gauging try to create like a singular focus.
No, here gauging, I'm going to tell you, like, I'm going to explain gauging by like introducing a gauge field and see whether there is a inconsistency in doing so. Yeah.
It's equivalent.
It's equivalent, yeah. I'll just give you a different way to do a similar thing, yeah. So I'm going to tell you there's a problem if you want to introduce a two-function gauge field. So now the two-function gauge field will take value in Zn. So you can think of the two-function gauge field as a special case of U1, the two-function gauge field, where the holonomy is like 0, or like multiple of 2 pi over n. Okay. And a way to introduce the two-function gauge field is to couple the, well, let's first say the U1 gauge field is small b. Now the symmetry is generated by like the basic Wilson of B, and therefore if you turn on a background gauge field for this one-function symmetry, then you just add a term that couples the like small b to the capital B. Okay. And then you ask if the action is invariant under the one-function transformation. So the one-function transformation. So one-function transformation is going to transform this Wilson line, and therefore it's a shift symmetry of the gauge field. So like you shift the gauge field by some gauge parameter, and then you transform the gauge field. You transform the background gauge field in a similar way. But you can immediately see that under the transformation, no matter like what kind of transformation you use, the action is non-invariant. Okay. In particular, there's going to be a term which is 1 over 4 pi, like lambda d lambda. So, well, let me just do it slowly. So if you perform this transformation, you got this term, and then over 2 pi b d lambda. So that's from the transformation of the first term. And the transformation of the second term will give you over 2 pi. This is lambda b. And then there's a minus over 2 pi b d lambda. And then there's a minus over 2 pi lambda d lambda. Okay. So this term cancels with this term. But you can still see that there are some terms that remain. So in general, the action with the background field is not invariant under the one-function transformation, and therefore the one-function symmetry is anomalous. But there's a fix if you introduce a bulk. So as I said earlier, so one way to describe the anomaly is by introducing the bulk. So the bulk will describe how the symmetry defects, like what's the coefficient function of the symmetry defects. So you have a bulk, and you have a boundary with some boundary condition, and the anomaly on the boundary will be described by the bulk, by the anomaly flow. Okay. So what's the bulk in this case? So this is 3D. And then you can add a 4D term. So let me just move it here. So the bulk in this case is quadratic in the background gauge field. So if you couple the 3D theory with the 4D bulk with this particular bulk term, then you can see that under this transformation, the bulk term will going to produce a boundary term such that the transformation will compensate each other. So for example, well, it depends. So for example, here under this transformation, well, let me just write it down. So this bulk term will contribute a boundary term which is over 2 pi w. And then there's also a boundary term which is plus over, well, maybe you have a put a minus somewhere, 4 pi lambda d lambda. Okay. And it will transform in such a way that the bulk term, the boundary term come from the boundary transformation coming from the bulk term exactly compensate the transformation, the number transformation on the boundary. Okay.
So is the 3D backup there would be like full back of the bulk back?
So yeah, it's a restriction of the bulk two-form gauge field to the boundary. Yeah, yeah. Now, more generally, there's a canonical construction of the bulk that describes the anomaly. So if you have a 2% DTKFT, and there's a corresponding 3% DKFT in the bulk that describes the anomaly for the high-function symmetry that corresponds to the DKFT. And the theory in the book is called the Volkmann model. Well, let me just tell you what the wave function of the model looks like without telling you the detail of the model. So the idea is that in 2% DTKFT, you are going to have many particles, and they can fuse in a different way or braid in a different way. Like there's a braiding and fusion of particles that consists of the correlation functions in the DKFT. And in the book, you are going to have the ground state wave function that describes some loop excitation. So there's going to be, you can imagine there's some loop. For example, you can have single loop or like multiple loop. So this is the wave function in the 3% dimension. And this loop can like fuse or braid with each other. And each loop in a bulk corresponds to a particle on the boundary. And the fusion and braiding of the particles tells you the relative weight when you write down the ground state wave function in terms of like summing over like different amplitude for the loop excitation. Like the like if you have two distinct loops here versus the loop like braided with each other, they're going to differ by a phase or by a number. That tells you how the corresponding particles in the TKFT braid with each other. Okay. So that's basically what the ground state wave function looks like in this 3% DTKFT. Okay.
Sorry, the loops are in 40 book, right?
This is a 40 book, yeah.
And the lines, is there lines of 40 of the topology always one thing?
So this is loop excitation, yeah.
So
this is loop excitation in 3D space.
Oh,
yeah.
So just to be clear, sorry, you're taking the 40 bulk and generating a state on its boundary.
Well, you can just say the state of the book, yeah. I mean, well, you can just think about it as a state in the 40 box area. But indeed, you can think of the state as some like correspond to some boundary condition. That's basically how the two things are related. Yeah.
Okay. The state of the boundary is this length.
It tells you the like various amplitude or various correlation function in the TKFT. Yeah. So in particular, if you start from the Zn one-function symmetry or those Zn like those Zn or this U1 level abelian transformer theory, you can construct the corresponding Volkmann model, and the corresponding Volkmann model is going to be described by this particular bulk term. Okay. Okay, let's see. I think that's more or less what I want to say today. So yeah, maybe let me just briefly recap. So today I told you like several applications of higher function symmetry. You can detect phase transition in like QCD, or it can tell you how to formulate topological orders in terms of anomalous and spontaneously broken higher function symmetry. And in particular, you can describe those anomalies. You can describe those anomalies using a TFT in the bulk, as shown here concretely, or more generally, it can be described by something called workable model. Yeah. So let me just stop here.